Hello, in this second revision lesson we're going to look at differentiation, including the chain rule, the product rule and the quotient rule. Let's get started then. This is something you looked at earlier on in Year 12 and we covered it again in this chapter just to remind you of it and to then use it to derive from first principles how you can differentiate sine and cos. Okay, so we use it, it's called the gradient function. Alright, so we have the f dash of x is equal to the limit as h tends to 0 of f of x plus h minus the f of x over h. Okay, and that can be used to find the gradient of the curve for any value of x. And when we use this, we call it differentiating from first principles. It's something that this is in the formula booklet, and it will be something you may be asked to use, for example, to prove that the differential of sine x is cos x, and that's something we looked at in this chapter. I'm not going to go over that again today, so go back and have a look at your notes on how you can prove that. So we did go and have a look at differentiating sine and cos, and we saw that if y equals sine x, then the differential of that, the dy dx, equals cos x. And similarly, if y equals cos x, then the differential of that, dy dx, is minus sine x. Alright. Remember, we have used the small angle approximations in our proof for this, our derivation of it, so x must be in radians, because the small angle approximations use radians. Similarly, we carried on and we saw that if y equals sine kx, then dy dx equals k cos kx. So for example, if I had y equals sine 4x, then dy dx will equal 4 sine 4x. Okay, and the same for cos. If y equals cos kx, then dy dx equals minus k sine kx. Right, so another example, if y equals cos of 6x, then dy dx equals minus 6 sine 6x. I've just seen that that should be a cos. Okay. Carrying on then, we went to look at exponentials and logarithms and how they can be differentiated. We had the special case of if y equals e to the x, then dy dx equals e to the x. Okay, so they are the same. So y and dy dx for e to the x are the same. And then we had a look again, we then put that constant in front of the x, and we found that dy dx, similarly to the trigonometry, that constant comes down to the front, so we have k e to the kx. Alright. Now we have if y equals ln, so the natural logarithm of a function of x, then dy dx will equal the differential of that function, so f dash of x, over the original function. So an example of that, let's say I have y equals ln x to the 6. Okay, then my dy dx is going to equal the differential of that, which is 6x to the power 5, over the original value, x to the 6. Okay, which I can simplify down to 6 over x. Alright, and then we had if y equals a to the kx, then dy dx equals a to the kx k ln a, for where k is a real constant and a is above greater than 0. So to write that in a more simple form, if I just had y equals a to the x, I would get dy dx equals a to the x ln a. Okay, so bringing that k in brings that constant down to the front. Alright then, so that was it differentiating individual terms. So a single exponential on its own, a single logarithm on its own, a single trig function on its own. However, the functions that we're going to start looking at now have got different combinations of these, and so we need, depending on the combination, we're going to use different laws and different rules to help us differentiate those. And the first one we're going to look at is the chain rule. So we can use the chain rule to differentiate composite functions or a function of a function. All right, one example would be y equals 2x plus 3 and then that all squared, okay, or maybe even a squared in here as well. All right, we could use the chain rule to differentiate that for us. And the chain rule states that dy dx equals dy du times du dx. You can see that with cross multiplication here, that simplifies down to dy dx, where y is a function of u and u is a function of x. So for example, we could substitute in, we could say u equals 2x squared plus 3, and therefore y would equal u squared. So you can see where y is now a function of u, and u is a function of x. We can differentiate these, u with respect to x and y with respect to u, and multiply them together, and that will give us our dy dx. The next rule we looked at is the product rule. Okay, so this enables us to differentiate the product of two functions. So for example, if I had e to the x multiplied by sine 2x, okay, so I've got a function here and I've got a function here. So that could be my u, that could be my v, and I can use the product rule here, so u dv dx plus v du dx. So another way of thinking that is leave one, differentiate the other, and then leave that other one and differentiate the first. Okay, and add those two together. So everything so far, apart from that first differentiating for first principles, a gradient function, none of the rest of these have been in the formula book, or will be in the formula book. So all of your trigonometric functions, or your exponentials, logarithms, the chain rule and the product rule, none of those are in the formula book, so you do need to learn them and be able to recall them. The final one though, quotient rule, is in the formula book, all right? And this enables us to differentiate the quotient of two functions. So when one function is being divided by the other. Okay. So if y is u over v, so going back to my last one, I could say y equals e to the x over sine 2x. Okay. I can now use the quotient rule, and that is dy dx equals v du dx minus u dv dx over v squared. This is in the formula book, okay, so u and v must be functions of x. It is in the formula book in this form here, so in function notation. So I can see here, so I've got f of x, so f dash of x times g of x, again that's my du dx times v, minus my f of x, which is my u, and my g dash of x, so dv dx, and then over g of x squared. Okay, so that one is in that formula book, but maybe not in the form that you might expect, in that you don't get it in this form. Okay, but it is there in function notation. Alright then, let's have a look at some questions. First one then. So given that f of x equals e to the minus x plus 2 ln x cubed, find f dash of x. Alright. So the first thing I'm going to do some manipulation of f of x. I'm going to keep the e to the minus x as is. I'm quite happy with differentiating that. And then, but what I'm going to do is I'm actually going to bring this up into ln x to the power of 6. Okay. So now I've got my f dash of x. I'm checking I don't need to use any of the chain product or quotient rules that I've just looked at, because none of these are either a function of a function or a product or a quotient of each other. They're just single terms. So I can go back to the first few slides that I looked at. E to the minus x, well, that I've got a minus 1 here as my k, so I bring that down to the front, so I get minus e to the minus x. Okay, and then here my ln x, ln x to the power 6. I do my f dash of x, so 6x to the 5 divided by the original function x to the 6. Okay, and so that leaves me with, simplifying this up and tidying up, I get minus e to the minus x plus 6 over x. And there's my answer. Moving on to the next question then. If f of x equals 3 sine squared x minus 2 cos squared x, show that the equation of the tangent to the curve with equation y equals f of x at the point Q, which has got x coordinate minus 5 pi over 6, is equal to 12y minus 30 root 3x plus 25 pi root 3 plus 9 equals 0. Okay, so this seems quite complicated, and it seems that there are two parts to this question. The first part is I'm going to need to differentiate this. Okay, and then the second part is working back to one of the first chapters you did in year 12. Really, is then once I find the gradient of this using dy dx, I will then start substituting in using y minus y1 equals mx minus x1. So that's my end goal, is that I need to get all the information I need to do this. Okay, and the first one I'm going to look at is my gradient, and to get the gradient I'm going to differentiate this. So the first thing I'm going to do, I'm going to look at them separately, because these are two separate terms. So I'm going to look at the differential of 3 sine squared x first. So I have y equals 3, and then here I have sine x all squared. Alright. Now this is a function of a function, so I'm going to use the chain rule. So I'm going to have dy dx equals dy du times du dx. Alright, let's do my side working. So I would say u equals sine x. Okay, so du dx equals cos x. And then I'll have, therefore, y as a function of u is 3u squared. So dy du equals 6u. Alright, so therefore substituting those back into here, I get 6u, so dy dx even, equals 6u times cos x. Alright, I'm substitute back in for u, so dy dx here equals 6 sine x cos x. So that's my first part. Now let's look at this one. I'm going to take y equals minus 2 cos x with that all squared. I'm going to, similarly from last time, I'm going to do u equals cos x. So therefore dy du, sorry, not dy du, du dx equals minus sine x. Alright, and so substituting my u in to this y equation, I get y equals minus 2u squared. So therefore dy du equals minus 4u. So I write down my chain rule again, dy dx equals dy du times du dx. Substituting in, dy du is minus 4u multiplied by minus sine x. Okay, and then bringing my u back, so my u here I've said that's equal to cos x, minus 4 u times minus sine x, I will get 4 cos x sine x. Alright. Bringing this back all together now, my final function, I need to add these together now because I brought this minus with me. Okay, so I can do dy dx equals 6 sine x cos x plus 4 cos x sine x, which overall gives me 10 cos x sine x. Okay, so now I've now got my formula or my expression that will allow me to calculate the gradient at any given point of x. So we'll continue on. So I'll just write down that my dy dx again, which is 10 cos x sine x. Okay. So now I need, so going back to my y minus y1 equals mx minus x1. Okay. When x1 equals minus 5 pi over 6, I substitute into here and I get y1 equals minus 3/4. Okay, so that's substituting in the f of minus 5 pi over 6. Okay, and then also substituting in, so dy dx at minus 5 pi over 6 equals 10 cos minus 5 pi over 6 times sine minus 5 pi over 6, which gives me 5√3 over 2. Okay. So now I have everything I need. So that's my m. So let's look at the equation. So y minus 3/4, so plus 3/4, equals m, so 5√3 over 2, x minus 5 pi over 6, so I'll add it. Okay, so we've now got to move from this equation here to try and find this equation here. Alright, so let's start by expanding everything out. So I get y plus 3 over 4 equals 5√3 x over 2 plus 25 pi times √3 over 12. Okay, so I'm starting to get somewhere. I've got this 25 pi √3, which I can see up here. Just giving a quick peek. So if I bring everything over, I will get y plus 3 over 4 minus 5√3 x over 2 minus 25 pi √3 over 12 equals 0. Okay. Coming up here, I want 12y, so I'm going to try and multiply everything by 12. So if I can write then 12y plus 3/4 times 12 gives me 9. 5 root 3x over 2, if I multiply that by 12, I need to multiply this top by 6. Okay, so that gives me 30 root 3x, and then this is 25 pi root 3 equals 0, which is what I have up here. Slightly different order, I need to move that 9 to the end. Okay, so that, just to make clear, that last step going from there to there, I've multiplied each term by 12. Okay, so I get 12y, I get 9. This 5 root 3x over 2, if I multiply that by 12, I'll have 12 lots of that over, but then 12 over 2 becomes 6, so I get 6 times 5, which is 30. And then I have this one multiplied by 12, I just get rid of the denominator. I end up with the equation that I wanted. Okay, next question then. Curve has an equation of y equals 2x to the power 4, all multiplied by 2 minus 5x squared to the power 3. So I need to show that dy dx equals x cubed, then open brackets 2 minus 5x, that all to the power n, and then open brackets ax squared plus bx plus c, where n, a, b and c are constants to be found. So it's a differential. Alright, but looking at it, this is a function of x, 2x to the power 4, multiplied by another function of x, 2 minus 5x squared, all to the power 3. So I want to use the product rule. Alright, so if I can write that here, so I've got y equals uv, so my dy dx is going to be u dv dx plus v du dx. Alright, so now let's try and find all these terms. I've already said I'm going to split this up into u equals 2x to the 4. Alright, so du dx is going to equal 8x. Alright, my v equals 2 minus 5x squared all cubed. Alright, so my dv dx is going to equal dv dA using a chain rule, but no, I'm not using u just to make sure I'm not confusing myself with this u up here, multiplied by dA dx. Okay, I'll have a equals 2 minus 5x squared. So therefore dA dx equals minus 10x. My v now equals a cubed, so dv dA equals 3a squared. Combining these together now, I get 3a squared times minus 10x, which gives me minus 30x multiplied by my original a, which is here, 2 minus 5x squared, 2 minus 5x squared, and that is all squared. Okay, so I have my u, 2x to the 4, I have my du dx, 8x, I have my v, 2 minus 5x squared all to the power 3, and I have my dv dx, minus 30x, 2 minus 5x squared all squared. So now I need to combine these with using the product rule here. So dy dx equals u, 2x to the 4, times dv dx, which is here, times minus 30x, 2 minus 5x squared, all squared, plus v is here, 2 minus 5x squared, all cubed, plus du dx, which is 8x. Sorry, multiplied by 8x. Okay, so let's simplify this down a little bit. I've got minus 60 x to the 5, 2 minus 5x squared, all squared, and then I'm adding 8x, 2 minus 5x squared, cubed. I've just checked, I have made a little mistake here, look, there's 2x to the 4. You've probably all been screaming at me since I made this mistake, but I've got 2x to the 4 here, it should be 8x cubed. Okay, so this becomes cubed here, and this becomes cubed here. Alright. Now, if this is where I'm now going to look at this show that and see where they want me to go with it. And they see I've got my 2 minus 5x. That should be a squared in there. Okay, that's a typo in the question. I'm not making this up. I've checked the answers as well. There is a typo in the question there, so there should be a squared. So I'm looking at my x cubed, and then I've got a 2 minus 5x squared to the power n. So I've got this bracket in both of these, and I've got an x cubed in both. An x to the 5 here, but there's an x cubed in there, a factor of x cubed at least. So if I take this out, I'm going to take that factor out. So I'll get x cubed, and then 2 to the minus 5x squared. What power can I take this to? Well, the lowest power, so therefore the highest factor is a squared here. So I can put that squared. Now let's open a bracket and let's look at this. I get minus 60 x squared. Okay, I've taken a factor of x cubed out of that one, so I get minus 60x squared left. And then here I've taken that whole factor out, so I don't get anything else. So I just multiply by 1 there. Then I need to add here. I've taken the x cubed out completely, so I get 8 lots of, but I still have one bracket of this, 2 minus 5x squared. Okay, so let's just check that just to make sure we're all understanding that. I've taken a factor of x cubed 2 to the minus 5x squared or squared out of each of these terms here, so the minus 60x to the 5 and the x cubed with the bracket. Okay, so taking it out, I get my minus 60x squared, and then this is the complete factor, so it turns to 1, and then I've taken my x cubed out of here, so I get 8, and I've taken a square of this bracket, not the cube, so I am left with one of the brackets left. Alright, so straight away I can see I've got my x cubed 2 minus 5x squared all squared, so it looks like n is going to be 2. Okay, now let's look at this bracket. I've got minus 60x squared plus, let's do 16, 8 times 2, and then 8 times minus 5x squared is minus 40x squared. Alright, and finally looking at that, I get x cubed 2 minus 5x squared and then minus 60x squared minus 40x squared minus 100x squared plus 0x. Okay, I could even write that for 0x plus 16. Okay, so n equals 2, a equals minus 100, b equals 0, and c equals 16. Alright then, now let's look at b. I'll write up my dy dx. Just so I've got that as a reference here. X cubed 2 minus 5x squared all squared, and then minus 100x squared plus 16. In fact, what I'll do with that one is I'll write it as this, which you will come clearer in a second. 16 minus 100 x squared. Okay, so that's my dy dx. Part B here is asking, find the exact x-coordinates of the stationary points of C. Now at the stationary points of C, the gradient is going to equal 0, so therefore dy dx will equal 0. So therefore all of this is going to equal 0. Okay, so at stationary points, dy dx equals 0, so therefore x cubed 2 minus 5x squared squared, and then 16 minus 100x squared equals 0. So I've got three terms here, x cubed, the 2 minus 5x squared or squared, and the 16 minus 100x squared, all multiplied together, and they equal 0. Okay, I've been asked for the x coordinate, so I want to solve for x. So if these are all multiplied together to equal 0, one of these must equal 0. So either x cubed equals 0, so therefore x equals 0. 2 minus 5x squared must equal 0. Okay, and this is a repeated root. All right. So therefore 5x squared must equal 2. X squared equals 2 over 5. So x will be plus or minus the square root of 2/5. Okay, and then 16 minus 100x squared must equal 0. Alright, now what's this an example of? 16 is a square number, 100 is a square number, x squared is a square number, so I get the difference of two squares. So 4 plus, not 100, 4 plus 10x, 4 minus 10x equals 0. Okay, and that gives me x equals 0 minus 0.4, or x equals 0.4. And there are my answers. Okay, so x equals 0, x equals plus or minus a square root of 2 over 5, x equals minus 0.4, and x equals 0.4. Alright, so if you use my dy dx, I know that at the stationary points dy dx must equal 0, and I've used these brackets here to find my values of x. Let's move on. Given that y equals sine squared x over e to the 2x, find dy dx. So which rule are we going to look at now? Well, I've got the quotient of two functions of x. I've got sine squared x divided by e to the 2x. So I'm going to use the quotient rule. Okay, I've got y equals u over v. So dy dx is going to equal v u dx minus u dv dx all over v squared. Alright, so let's look at my side working. I'll have u equals sine x all squared. So this is a composite function, so I'm going to use the chain rule. So du dx equals, again I'll use du dA to stop confusing myself with the v here, times dA dx, okay, where a equals sine x, so therefore dA dx equals cos x, and then u equals a squared, so du dx equals 2a, sorry, du dA even. Alright, so therefore du dx equals du dA, which I have as 2a, multiplied by dA dx, which is cos x. Alright. So therefore I have 2a, I substitute my a back in, I have 2 sin x cos x. Okay, there's my du dx. Now let's look at v. So v is e to the 2x, so dv dx equals 2e to the 2x. And then something I like to do is just to write my v squared down as well, so I get my v squared as e to the 4x. Okay. So I have my u as sin squared x, I have my du dx as 2 sin x cos x, I have my v as e to the 2x, my dv dx as 2e to the 2x, and my v squared as e to the 4x. So let's substitute everything in now. So dy dx equals v, which is, dy dx equals v, which is e to the 2x, times du dx, which is 2 sin x cos x, minus u, which is sin squared x, dv dx, which is 2e to the 2x, all over v squared, which is e to the 4x. Alright, simplifying that down, I'll take a factor of e to the 2x and, 2 sin x e to the 2x, so 2 sin x e to the 2x, okay, I've got e to the 2x, I've got a 2, I've got a sine in each one. That will be cos x here, minus 2, no, don't need the 2, just sin x, over e to the 4x, okay. And then I can even simplify further by taking e to the 2x out and having this e to the 2x here. Right then, final question. We're going to differentiate e to the 4x with, over x minus 5 with respect to x. Alright. So again, I've got a quotient, so I'm going to use the quotient rule. So dy dx equals e to the 4x. Sorry, dy dx equals v du dx minus u dv dx over v squared. Okay, so u is e to the 4x, so therefore du dx is 4e to the 4x. Alright, v I'm going to have as x squared minus 5x. Okay, just expanding that bracket. So dv dx equals 2x minus 5. Okay, and then my v squared, I'll just leave it as x squared minus 5x all squared for the moment. Okay, so now substituting in, I get dy dx equals v, which is x squared minus 5x, times du dx, which is 4e to the 4x, minus u, which is e to the 4x, dv dx, which I have as 2x minus 5, all over v squared, which I have x squared minus 5x, all squared. Okay. Simplifying that down, I can take a factor of e to the 4x out, so I get e to the 4x squared minus 20x minus 2x plus 5. Okay, and all that is going to be over x squared minus 5x squared. There's a bit more in terms of factorization. Maybe you could do with this. You could expand and compare those. So it's going to be that, isn't it? Okay. You could then bring these together, maybe factorize that, and see if you can get any factors out from the underside, from the denominator. But that is fine for now. All right. So that's differentiation done. You can see that some of the questions you're using a multitude of the rules. Okay, so if we go back to, for example, the previous slide where I had the sine squared x as part of my u. Okay, so you will have to, one, identify the rule you're going to use first, and then once you start getting into that, see if there are any more that you then need to use. All right. So it's building on skills that you've learned already and breaking it down into simple differentiations each time. Okay, thank you for listening. I'll see you soon.